please, Daniele, when you're ready.
Can I share my video or something like that?
Yes.
Okay.
Please.
So first of all, good morning, everybody. Thank you so much to the organizer, to Michele and Danilo for inviting me here to share my thoughts about this topic of climate change and water resources in the mountain. I will try and open the presentation. Okay. Do you see my screen now, the presentation?
Yeah, we see the screen, yes.
Okay. So today, as reported, I'm going to talk a little bit about climate change and the fallout of this phenomenon upon the mountain, with particular attention to issues related to water, namely to the hydrological budget and the cryospheric budget, and how this affects life in the mountain in many ways. Also, I will say something about hydropower issues, but basically these come in the wake of, let's say, variation and changes to the hydrology of the mountains. Here you can see already some picture of different places in the world, basically all having in common some traits, specifically high altitude. Hydrology, for those who are maybe with an hydrological background, and even for those who aren't, historically is a science that was born and developed in the 50s, 60s, so it's a relatively young science, at least from the engineering point of view, and it was mainly devoted and focused on the hydrology of the arid or semi-arid areas. But in the last 30 years, I would say, 20 years or so, it's being initially and changing, focusing on the mountain, which is on the high altitude, and the effect of the cryosphere, which is the dynamic of snow and ice in the mountain, and how this interacts with the water budget and the hydrology. And, well, in the last 10 years or so, maybe 15 years or so, also studying the effects of climate change, because even though the issue of climate change is becoming very popular in the last few years or so, maybe with Greta Thunberg and also other movements and phenomena, in reality, at least in the last 15 or 10 years or so, scientists, hydrologists, and others are startingly developing science and investigation about how this impacts, in fact, the hydrology of the high altitude. I just want to mention this a number of logos here. We are cooperating with this committee, which is called EVK2CNR, and it's a committee based in Bergamo, who has a very interesting activity of research in the high altitudes, and specifically with the SHARE project, which is science in high altitude. Namely in Pakistan and Nepal, also in cooperation with ISIMO, the very famous institution for research in the mountain, etc. And Polytechnic of Milan as a sort of joint venture, or better, it's a part of this foundation, which is called CMCC, which is the Centro Euro-Mediterraneo per i Cambiamenti Climatici, or the Euro-Mediterranean Center for Climate Change, which is an institution of Italy explicitly dedicated to the study and investigation of climate change and their impacts. So just to make a little bit of a focus on the current activity of Polytechnic. This is a group which was established some years ago. We call it PolyHigh Group, which is people in the Polytechnic working in the high altitude. There are a number of persons here that have been in the past cooperating and are now cooperating with me in this activity. We also, well, this is Andrea Sancini in the mountain, and we have this guy here, which is called Leonardo Stucchi, who, by the way, is a runner. Is a very skilled runner, and he recently conquered the Adamello Mountain of Italy, so he's also participating in our activity, but by the way, he's also a PhD student. We have a number of honorary members of the POLIMI group, and here, well, we have Michele Frepaz, who is, I'm not even sure if he knows, but he's an honorary member of the group, and we cooperate with a number of institutes in Italy and elsewhere, and with University Milano in the field of glaciology, etc., and University Torino in the field of avalanche science and other activities. When I open up the WebEx tool a few minutes ago, Michele was talking, in fact, about avalanche, and we are cooperating about this topic in the last few years also. So it's a real pleasure also to be here with these friends from Torino. Well, a number of activity here. I will just say something about, well, everybody knows about climate change. What is the meaning of this issue? Well, recently I just met a joke or a sort of a small balloon on the internet. Maybe somebody put it on Facebook. I don't remember who exactly. Maybe even Danilo, possibly, because he has a very intense activity on Facebook in reality. And this was something about. Don't ask people if they believe in climate change, just ask them if they understand, because it's not a matter of belief and it's not Santa Claus, but it's science. So you simply have to understand that. The main message being that in reality, well, climate change is real and it's ongoing, and we have to start, facing the real truth that we have to mitigate and we have to adapt. Here, just a picture on the bottom right with the global temperature at the monthly scale worldwide. And as you can see, there is a very large drift. Well, this is stopping at 2016, but in reality, we know that in the last few years, temperature is increasing by the day, in fact, by the year. And we are reaching very quickly the 1.5 target, which, by the way, is the target set out by the Paris Agreement at the end of 2015, and we expect that within the century we should be able to limit the growth of temperature below 1.5. Here's some motivation for the study, for the things that I'm presenting, and this is mostly based on my activity and my group activity in the last, I would say, 15 years or so, connected to water and hydrology in the high altitudes and in the mountains. So I will present some of our results in order to represent with visible evidence what is the impact of the climate, the global warming and the climate change in the mountains, what are the evidence, and even what are the potential future and vision by scientists based on what we call projection, and we will see about that. I will also say something about this being all pleonastic or not, meaning that, well, these changes may impact really life in the mountain and economy, etc. And we will say something about that. Sometimes we talk about hydrology of the mountain, and I will a little bit make a mix between this concept and the concept of middle latitude hydrology, because as we will see, these facet of mountain hydrology has some interest, especially in the mid latitude, which is in the intermediate climate regions of the world, basically. Well, this is, for instance, a very first paper I want to represent. This is not from myself; it's been published 15 years ago. Now, as you can see, and well, in this paper, and you see a number of green catchments worldwide here, and the authors studied a number of catchments worldwide, these green ones, and what they studied was the contribution of ice melt, which is the melting of glacier in those catchments, and how much this impacted the hydrology of the area, and especially how much this impacted the population there. They made a very simple calculation, which is during summer, they calculate the share of ice melt coming from the mountain to the total amount of water in the river. And then they multiply this time the population living in the basin. And as you can see, they call these things PIX, PIX, which is a population index, and they classified with a ranking the catchments worldwide based on this number. An interesting thing that I can, for instance, share with the Italian people following is that the Po River, which is our main river, our common river for people in northern Italy, from Torino, Milano, etc. It's the fourth in the ranking. It's a low value here in reality with respect to other catchments, but still it's fourth, meaning that water coming from ice melt during summer is important for us. Then we have other catchments. Well, the one with the highest ranking are in this part of the world, which is Middle East or Central Asia, but there are also a number in other regions, for instance, in North America, even in South America, etc. However, this is not a complete study because, as you can see, they just took some samples. I mean, they didn't take all of the glacier ice catchment worldwide, of course. So, temperate mountain hydrology, in my view and in my personal experience, of course, I might be wrong, has some interesting in a certain belt, in two belts mainly that are the temperate regions, where basically the local hydrology may be affected by the presence of cryospheric areas, which is ice and especially snow, seasonal snow, which is falling during winter and then being melted during summer, and this may contribute relatively well to the hydrology of the rivers. I should say that some exception may be related to Central Africa because some of the rivers here, including the Nile River, for instance, are somewhat fed or watered by snow and ice melting in some high altitude mountains here in the center of Africa. So this might be a notable exception in reality. Anyway, generally speaking, these belts highlighted here are those where more or less the influence of ice melting and the cryosphere seems more relevant. Well, I don't want to bother you with a number of equations from engineering hydrology, but anyway, I want to represent a little bit the reason why we think that the inclusion of the cryosphere and especially of the dynamics of glacier ice bodies and ice cover and ice field, etc., is of interest. Well, we can do so by introducing a little bit of equations related to the meaning and functioning of the hydrological cycle. First of all, we can define the reference volume or the reference control volume, which is the one you see here, which is, we could say, the representation in a three-dimensional fashion, a little bit of a baby representation, in fact, but I think understandable, of a catchment, indicating basically that the hydrological catchment is a portion of the territory, basically, where you have some inputs, mainly of precipitation, that can be rainfall or snowfall. You have some other hydrological phenomena, and these are mainly evapotranspiration, divided by transpiration and evaporation, and this is called hydrological loss, or these are called hydrological losses, meaning that this water goes back in the atmosphere and feed again the atmospheric hydrological cycle. And then you have some, well, the most important terms from some point of view, which is this flow outside of the catchment, which is basically the integral of all of the occurrences and phenomena that happen in the catchment. And this is what some way interests the mankind and the people, because you can take this water and use it for a number of purposes, hopefully with some respect to the ecology of the environment, which is application and understanding of the hydrologic or of the ecological flow in the catchment, of course. Well, these thing may be represented in a way which may be very complex or very simple, also depending on the degree of knowledge of the processes occurring and of degree of capacity of measuring all of these phenomena into the catchment. One way that we often do is the one you see here. And the interesting thing about the hydrological budget is that what we call the control variable or the main variable is what this thing here, which is S, and we call it the storage. Storage means the amount of water which is basically stored temporarily for some period within the catchment. So we model basically the dynamic in time of an hydrological catchment of a water basin by the changes in storage within the basin itself. This can be on the surface, for instance, in lake or even in the river network itself, and also into the soil. In the deeper, so in the first layers of soil or even deep down. This is not very well defined, but anyway, we can imagine that some part of the underground soil is contributing also to the hydrological flows. We define main input, R, which is the rainfall, which is the liquid form of precipitation. We define MS, which is the melt of snow, which you can see here in these high altitude caps, minus the evapotranspiration, which is the main loss, minus Q, which is the amount of water flowing out of the catchment. Those phenomena are all basically seasonal. And if we reduce the seasonality, or if we consider only, for instance, the extent of scale of 1 year, which is what happens from 1 year to the other, or at the yearly scale. So if we neglect seasonal patterns, we can even write down an equation like this, because we can assume that the storage doesn't change a lot, and we can assume that all snow is melted during 1 year, because we know that the behavior of snow melt is seasonal. So we can change a little bit and write this equation very easily, and we call P the total precipitation, be it rainfall or snowfall. And we can say that in one basin in 1 year, all the precipitation is used for having stream flow or hydrological losses, which is evapotranspiration. So we can write down this equation as here. Well, evapotranspiration is basically what happens with the vegetation and the soil, which is water which is in the soil. If there is a certain temperature, if there is a certain solar radiation, which is driving a lot of this phenomena, and also if there is wind, all of these phenomena drive evaporation from the soil. And at the same time, they drive transpiration from the plants. The plants pump water from the soil by suction. They have a suction power, so they can extract water from the soil. They use this for their biological cycle, and then they release it as a water vapor in the atmosphere, basically. And this is evapotranspiration. Well, this A here means actual, but never mind. So let's have a look at this paper here, this graphic here, this chart here. This is called Boudico chart or Boudico curve, and it's a lumped way to describe the behavior of certain catchments in terms of duration between basically the potential for evapotranspiration given the climate and the real evapotranspiration given by the total precipitation. Without entering too much, we can say that this curve here basically divides catchments and regions in regions that are energy limited or in regions that are water limited. Energy limited meaning there is a lot of precipitation, but because the climate is too warm, it is too cold, basically, or too chill, there is not much of evapotranspiration. So most of the water becomes runoff. Other regions that are water limited have the vice versa problem, which is they have little precipitation and a dry climate, a climate basically resulting into a large potential evapotranspiration. So basically these are the areas where there is too little precipitation with respect to the local climate, which is too hot, basically, and there is too little water. Well, many temperate regions basically fall within this under this curve, which is in water limited regions with a low amount of actual evapotranspiration, an high amount of actual evapotranspiration with respect to precipitation. So basically, they have too little water for the place they are. And this is the case with a number of arid or semi-arid catchments worldwide. And basically, the reason why these catchments still have some water in many cases is related to the mountain. Well, this is a picture of this concept, which is the simplification of the water budget at the yearly scale. Okay, so what happens with the glacier ice area, which is area where there is some permanent ice cover? Well, I have to remind myself, and I even can remind to you, but I think you know better, that our present geological era, and I'm not a geologist, so I don't know, I'm not very expert of that, and that's the reason why I'm saying that I need a chart like here to also explain or remind you of this concept. We are in the Quaternary, basically, and this is basically a glacial era or an ice age. And to even remind this, I put here this figure of the ice age and the dinner with dodos. For those of you who haven't seen it, in the ice age, there is a very interesting cartoon description of why the dodo get extinguished, basically. It's not the real reason, but it's very funny anyway. So the point is that we are basically in a glacial age or in an ice age. And if you look at this scale here, which is going from right to left backward in time, so in thousands of years from now, or in millions of years from now, etc. So it's a logarithmic scale. You can see that in the past, for instance, 500 millions or so of years ago, temperature on the Earth, which is this line here, was very, very high. Here you have the temperature with reference to the 30 years, 96 and 99, and you can see that in reality, estimates of the temperature on this geological scale were very, very high, much higher than now in reality. And as I said, here we are in a sort of an ice age. The cycles you see here are different glacial and interglacial periods. And in reality, the last 10,000 years or so, which is the time where basically we have the most registration, we have the most information, etc. It's basically, and when the story of man basically begins, that is when we can in fact retrieve and find information about man and its habits, etc. It's basically an era with a temperature oscillating around the zero. And it is expected, because the last glaciation was more or less 15,000 years ago, it is expecting that another glaciation is incoming, because there is an expectation that interglacial periods have a duration of 10 to 15,000 years or so. So basically, in some aspects, in some sense, we are on the verge of a new glaciation in reality. So we would expect that temperature would go down very much. However, in the last 10,000 years or so, which is what we call the Holocene, the age of everything, as the geologists used to call it, the point is that temperature has been oscillating a lot, but it's never been oscillating so fast and with a sudden increase of temperature like in the last 150 years, which is what we call the Anthropocene. They invented this new name for this period when basically the temperature and the climate on the Earth was influenced largely by the man, basically. That's the reason why scientists are so concerned. So this is to remind us that in some areas worldwide, not only we have the hydrological cycle as I have been depicting this above, but we also have some pieces of remnants of relics, in fact, of ice, of glaciers, basically being the relics or the remnants of the last glaciation, in fact. So glaciers have been retiring a lot, but still in some places, in the high altitudes and in the polar latitudes, we still have pieces of ice, large pieces of ice. And the point is that this ice is an extra source of water, which is stored water, or they call it water towers, water, canned water, etc. Is basically an extra amount of water, frozen, melting down slowly. And this water is in reality watering and feeding a lot of catchments in a number of places worldwide, especially in our Alps still, in North America, in the Andes, in Central Asia, etc. And these melting ice caps are still giving a lot of water, even in areas that would be arid or semi-arid, which is a probable, a likely lack of water which would happen in these areas is in reality offset by the presence of glaciers. So in the sketch here, in the cartoon, you have an extra amount of water basically coming from the melt of ice fields and of glaciers. So this is basically a sort of gift from this past glaciation, but the problem is with these glacier caps have been basically in a stable or dynamic equilibrium in the last 10,000 years, with a slight decrease and then slight increase, but basically on some sort of equilibrium, which meant input of precipitation and snow from the high altitude, melt at the low altitude, and a constant, more or less, size of the glacier and volume of the glacier, and with some continuous feeding downstream. The problem is this equilibrium has been basically offset by climate change, and the point is these ice caps are rapidly melting down and rapidly downwesting, and this is basically changing the water cycle in the mountains. This is an interesting picture, I think, from a catchment we are studying in the high altitude in Lombardia region. This is called the Dosde. Dosde catchment is in north of Bormio, for those who know the area, and this is called Dosde East Glacier. And on this stream here, which is the glacial stream, we put some measurement instruments and we made some measurement of stream flows in order to be able to quantify the hydrological budget. This is a small animation, and here I need to skip out of the presentation and I want to see you the movie. Well, again, the animation displays in the bottom panel the daily measured temperature and the daily measured temperature here in the lower panel in black and then red during the simulation, and the total precipitation, which is snow or ice, snow or rainfall, depending on the daily temperature. Here you will see snow water equivalent on the ground, which is snow that accumulates on the ground during winter and then goes away during summer. And when snow goes away during summer, you will have these red colors here on the right side, which is basically the ice cover, the glaciers of the area, basically being discovered, which is snow melts away, the ice remains in the sun, and basically this provides melting. And the red to yellow scale that you will see here is melting in millimeter per day. I'm trying to show this. Okay. You can see temperature here, precipitation, the snow water equivalent going down in winter, going up in summer. And with disappearance of the snow layer in summer, you will see ice melt here. Okay. Well, this is very fast, but now we are in summer, so the temperature is above zero, not too much above zero, because here we are 2,000 meters above the sea level, and yet much of the snow cover has left, and ice is starting to melt, basically. Okay, now the year is over, we go back to winter, a lot of snow, and so forth. You'll see here a lot of precipitation, but during the summer. So this will not help, basically. And again, winter. So the dynamic is quite clear. In fact, in the high mountain, you have precipitation during winter, and this is snow. This covers the ice. And if it persists in time for a long time, the ice is protected, and the snow melts slowly. But during climate change era, higher temperature than normal is providing very rapid snow melt, and very rapidly unshielding of the glacier, which is the glacier remains under the sun and melts faster, basically. So we have an imbalance of a former situation of equilibrium, which is now leading to faster melt. Well, we did some investigation recently related to a number of catchments in the Alps in order to evaluate whether or not the conjecture we were making basically in the field of hydrology, which is depending on different temperature and different precipitation regime under climate change and the melting of glacier, etc. Do we have a real trend in stream flows in the Alps, for instance? That is, water flows are really changing, are decreasing, increasing, etc. Because in reality, there were a lot of conjectures, there was a lot of reasoning about these topics, but not real investigation that we knew of in terms of hydrology. Well, what I'm showing here very, very rapidly is a map of all of these catchments that we studied. These are mostly in Lombardia region and in Trentino region, a little bit in Veneto region, and a few in reality in Piedmont region. We didn't have data about the Val d'Aosta Valley. I'm so sorry for Michele, maybe he was interested, but I think we could gather and investigate. Here we have JFM, which is January, February, and March. And here we have July, August, and September, which is summer. Well, basically, what we see here in this palette of colors is colors here in the JFM, which is winter period, colors in the order of nearby the green, sorry, the yellow and the red and the orange, etc. While here we see colors in the neighbor of the green and the yellow and the blue, etc. What does it mean? If you look at the palette here, which is at the scale, the colors going to red mean increase, and colors going to yellow and light blue, etc., mean decrease. Well, you can see clearly that during winter, we have an increase, and during summer, we have a decrease. A decrease of what? Well, this is a strange number, but this is in cubic meter per second, which is of the mean flow during that period per kilometer, per square kilometer. So it's a measure which is homogeneous between different catchments, because catchment with different magnitude cannot be compared if you do not consider a specific volume. Okay, so it's basically a flow in cubic meter per second per square kilometer, then multiplied by 10 to the 4, but this is just a scale factor. This basically means that during winter we have more flows, and during summer we have less. Why so? Well, one can expect that basically during winter you have less snow precipitation because the weather is too warm and you have more water. And during summer, in fact, you basically pay for the lack of snow during the winter, and because of the decreased size of the glacier in time, which basically provides less water. So during summer you are in a drier condition, and during winter you are in a wetter condition. Well, in reality, this is even true for fall, which is right where we are now, where in reality, increasing precipitation, liquid precipitation, and increasing stream flows are progressively being seen in the fall season in the North Alps. And well, the floods occurring in these last few days are in fact a plastic representation of this. In reality, fall and winter floods will be more and more frequent as we expect. I don't have the figure at the yearly scale, but at the yearly scale, discharge is basically decreasing because the overall effect is to have less amount of water in this river. Well, I'm skipping this. I will then send you the copy of the presentation, maybe in a PDF format, so you can browse it and have a look at it by yourself. Here, basically, what I'm demonstrating is that the higher the catchment, the greater the decrease of water availability, because in the higher catchment, the lack of snow and water and ice melt and water from ice melt is more visible and more felt. I wanted you to, are there any questions? If there is any question, you can ask or maybe write in the chat.
So Daniele, we usually continue for 45 minutes, and then we stop for 15 minutes for questions, and then we repeat for the next hour, if you agree.
Okay, perfect. Okay, but stop.
They are allowed to write already the question in the chat, so we note the question.
Okay, perfect. so stop me when it's time. I wanted to present this case of the anomalous Karakoram. Well, why they say anomalous? Because recently somebody postulated the presence of this Karakoram anomaly, and by this meaning that in the Karakoram area, which is, by the way, at the intersection of the northern part of Pakistan and Afghanistan, where there are this the meeting point of these three chains of mountains, which is Hindu Kush, Karakoram, and Himalaya, and we are particularly studying the northern part of Pakistan here, so the upper Karakoram. They postulated this anomaly, which is there. The glaciers are not melting away, there is no down wasting. So some years ago, we made this project called Paprika, which is an acronym for investigation of hydrology in the Karakoram, basically, in the high altitude area, in order to assess whether or not this was true, and in general to draw some data-based hydrological budget for the area. And database is a key word, is a key expression, because in reality there is a lack of data for the area, in particular from the hydrological point of view. Even though Pakistani authorities therein have been recording and making some field campaign in the last few years, but still is a very complex area, very high altitude area, so not much of information is available. Well, an interesting picture is here. This is the Baltore Glacier in the middle of the Karakoram, in fact. And this is a picture from 1954 by Ardito Desio, who was a very famous professor of geology at University of Milano and a very famous cartographist, etc. And he also drove an expedition in 1954, in fact, and was the expedition of the these Italian people that reached the summit of K2 for the first time. So this was an historical expedition. But let aside the climbing part, we have this picture. And if you look at the same picture taken in 2013 by this colleague of mine, Andrea Soncini, during one of these in situ field investigation that we had, well, you don't see much different. That rock here that you see in the circle is called Ardito Desio's rock, in fact. And well, it is normally used as a benchmark, as a milestone in order to assess the movement of the glacier, and in reality you don't see visually much difference. Well, we did a number of local investigation. In fact, we focus on this catchment that is called the Shigar Basin. The outlet of the catchment is here in this point, and it's exactly in a town, in a place called Shigar. And this catchment contains a lot of large glaciers. The most famous one being the Baltore Glacier here, in fact. And by the way, the K2 is more or less here, the K2 peak. And the other very famous is the Biafo-Ispar Glacier, which is this one here. The gateway to go to the Concordia summit, Concordia place, which is basically the base camp for climbing to VK2 and Gasherbruns and other mountain, can be reached from Ascoli walking 60 kilometers. This is Concordia, called Concordia Circle. To reach Ascoli, again, you have to drive for 4 hours from the closest place with an airport, which is Scardo, basically. Well, you can fly or you can do the Karakoram Highway, which is more or less 24 hours driving. And then you can go to Ascoli. Well, I just want to show you some pictures because it's a very nice area. This is Scardo, for instance. And this is our weekly walk to Concordia. And in any of these points here, where you see the pin here, we basically made some measurements. Well, unless from the K2 and Broad Peak, because of course this was just for a representation matter. And also Condogoro La, the pass, it's called the Condogoro Pass. We didn't go, but we measure a number of things in all these places here: ice melt, the brick over, and other things. Well, I'm just showing some in picture of the trek. These are the famous Strango Towers, very known to climbers. Well, interesting thing are glacial streams, which is on the Baltore Glacier, in spite of being basically a stable glacier or supposedly stable glacier, lots of these ice flows, of these ice crevasses and ice streams are present. These are called bedières, and well, basically they represent ice melting, basically. These are ice sails. In South America, they call these penitentes, in fact. And this is a nice table, which is again, or in Italy we say fungo di ghiaccio, or we say ice mushroom, but in English they say ice table. And again, it's 2 meters or so in depth, and this basically means that the ice has been melting in some period, maybe 1 year, maybe 2, by 2 meters or so. And the rock remaining, because it basically protects the underneath glacier from the ice. We will see that this type of melting in reality is reached in one year, more or less. And this is Concordia Circle. This is, I think, the Broad Peak here. It was 2011, and there were a few people. That the camp was quite empty in reality. In other years, it much more crowded. And this is the K2. We were lucky because it was very sunny days and we could see the mountains very well. And here are a number of measurements that we made. We measured discharge in a number of points. We put an hydrometric station in Shigar here. Basically, we revamped a station used there for a long time from the Pakistani Meteorological and Hydrological Department. And this was continued, I think, in the 2000 or so, and we reinstalled this. Now it's not operating anymore. And another, a Paju, 3,600 meters here, just downstream of the Braldo River, which is the glacier stream from the Baltoro Glacier. We did a number of surveys, which is, well, this is a steam drill that you see here. Steam drill is basically used to drill a hole within the ice, and these holes were 10 to 12 meters deep, and we put ice stakes, which is bamboo or plastic pieces, sticks of 2 meters or so, and they are connected. And every time the ice melts down, the stick emerges. So at the end of 1 year or 2 years, we went there for, I think, two subsequent years in 2012 and 2013, and we could measure how much the ice had melted by immersion of the stakes. This is a typically glaciologic method. Here, for instance, right bottom, they were measuring immersion of snow, because they went there in April and they could measure the amount of snow present basically at the end of the accumulation season. So we had a good measure of the amount of snow during the winter. Here they are mounting the hydrometric station on the Shigar River, and this is the hydrometric station in Paju River, which is into a canyon.
Okay, excuse me.
You can see some pictures. The Shigar River is 150 meters large, so measurements required a boat and a flow meter, etc.
Daniele, can you hear me?
See, yes.
Okay, if you agree, we can stop 10 minutes for questions.
Okay, perfect.
So if there are questions, please, it's don't be scared by formula.
You can even write in the chat. You think so?
Okay, maybe we can stop for 5 minutes, and they can let's say digest all the information and keep the question for the last break, if you agree.
Okay. Yes.
So I'm stopping now the recording, and we will see you in 5 minutes.
Okay.